Welcome back to another Daishinfinity video. In this video, we're going to talk about set theory and the specific operations that are valid in the set theory sets. So the first operation is a commutativity, and the second operation is associativity, and the third one is the distributive rule. So we have all three rules, and I would like to prove this to you guys by using some tricks. So first of all, we're going to prove the commutativity. Commutativity says that it doesn't matter what kind of row we have. So if we have A union with B, then we can say that B is also in union with A. Now, what is a union between two sets? A union between two sets, A and B, is having all of the sets that are in A and B. Okay, and it doesn't matter if you say A union with B or B union with A. This is the statement of this equation. So today I would like to prove this to you guys. Now, A union with B really says that is equivalent to saying that X is in A or X is in B. And B in union with A is equivalent to saying that X is in B or X is in A. Now, if X is in either A or B, let's say X is in A, then this statement will be true and this statement will be false. But since we have an OR, this is a true statement. And over here we have X is in B, so this is false. But we have an OR that makes us have the opportunity to choose for this one, which says that X is in A, because we have just chosen, for example, that X is in A. So this is also a true statement. And we have true statements on both sides. So we have just proven that it's equivalent to saying that B is in union with A. So we have proven this formula. Okay, now the second one states that if A intersects with B, B also intersects with A. Now, what is the intersection between two sets? The intersection between two sets A and B is the set, or the amount of elements that are contained in both sets. So X is in A and X is in B. So this is what we have to write. Okay, so for OX means that X, we can write A is in union in intersection with B, which is equivalent to saying that X is in A and X is in B. Okay, and the same thing for B intersects A, which is equivalent to saying X is in B and X is in A. Okay, let's say, for example, X is in A only. Then this is a true statement and this is a false statement. So it's a false statement. And this is also false and this is true. So true and false, which means false. Okay, logically saying both are false, and we have false, false. We have to try and see all of the combinations here. Let's say X is in B. Then this is a true statement. This is a false statement. This is a true statement. This is a false statement. So we have false, false statements, which is also equivalent to saying it. Now, if X is in neither A or B, then this is false, this is false, this is false, this is false. So we have false, false, which also says it's true, that the equivalence is true. And the last one is if X is in A and B, then this is true and this is true, so the statement is true. And this statement and this statement is also true, so this is true. So we have true, true. And for all the situations we have been analyzing, it's true that both of them are equivalent. So we can say that at the end, A intersecting B is the same thing as saying B intersecting A. So we have proven the commutativity. Okay. I hope you guys understand what I mean by this. Okay. Now the second one is associativity. We have two of them, but union and intersection. So if we have A union with B, union with C, it states that A is in union with B union C. Now what does it mean? It means that X is in as X is in A, or X is in B, or X is in C. Okay. Now we have just put the parentheses here and here, but it doesn't really matter where the parentheses are, since we have a statement of three statements, and since we have an or, it doesn't really matter where we put the statements. So it's just equivalent to saying X is in A, or X is in B, or X is in C. Okay? So this is why it actually works, since let's say X is only in B. Okay? We have to prove like for all of the cases. If X is in B, then this is false, this is true. Okay? And this is false. And this one says that this is false, this is true, this is false. So we have a true statement, since this is true and this is true for only one, for at least one. Now if we try every single case, this will work out. Okay, so the associativity works for the union. Let's try for the intersection. So A intersect B intersecting C will equal to A intersecting B intersecting C, which will state that X is in A and X is in B and X is in C. Okay. Now, if X is in A and X is in B and X is in C, we have the OR sign. If you have looked at the logic playlist, I have a few proving videos of this one by using the table. And like if we try to look for all the cases, it turns out that we can actually ignore the parentheses, how the parentheses is ordered. So we can actually say that X is in A and X is in B and X is in C. So at least we have also gotten the intersection for the associativity rule. Now the last rule is the very difficult rule, which is the distributive rule, which states that if we have A, so it's a mix of intersection and union. If we have A intersecting with B union with C, it means that we have A intersecting B or A intersecting C, union with A intersecting C. Now, this is a bit difficult, okay? It just tells us if we take the left-hand side, A intersecting B union with C, it's just equivalent to saying X is in A and X is in B or X is in C. Okay? Now, we have different kind of logic symbols, and or. Then we can see that if X is in A, only in A, then this is a true statement, okay? And this is false and false. So we have true and false. So it's false. Now let's look for this one. We have to write it down as the X form so that we can truly see what it means to be equivalent. So if this is equal to A intersecting B, which states that if that X is in A and X is in B, in parentheses, or x is in A and x is in C. Okay, so this is what we have to prove. Let's say x is in A. Then this is true, this is false, so it's false. Here, this is true, this is false. So true and false is already false. For false or true and false, which is false. So false or false will give you false. Okay? Let's try another one. Let's say x is in B. It's true, it's false, but it's an or, so it's true. And true and a false statement is a false statement. If x is in B on the second one, this is a true statement, false and true will give you false, or false, so false, or false will give you false. So false on both sides. Let's say x is in C. This will give you true, false, but the whole thing is true, and false, so the whole thing is false. If x is in C, this is false, and this is false, but this is true. But true and false will give you false, or false will give you false. So we have just proven for all the x is in A, B, C. That is actually true and equivalent. Now the second one. Let's say x is in A and B. Okay? If x is in A and B, then this is actually true, and this is false, since x is not in C. So this is false, and a true statement is false, and a true statement or a false statement will give you true statement. Now, the first one, x is in A, true, x is in B, true, false. So true or false will give you true, and true will give you true. So we have a true statement. Now we have to try and see if x is in A and C. So this will be true, false. False and true is true, and true is true, so it's true. If x is in A and C, this is true, this is false, so this is false. Or this is true and this is true, so this is a true statement. False or true is true. Okay. So true. Okay, perfect. And the last one, if x is in B and C. Obviously, if x is in none of them, it's false and false, so this is also equivalent. And if x is in B and C, this is true, and this is false, so this is a false statement. And if x is in B and C, this is true, but this is false, so this is false. And this is true, false, and this is true, but true and false will give you false. False or false will give you false. So false and false. And the last one, if x is in A, B, and C, then obviously it's a true statement and a true statement. So it has taken a long time until we actually proven all the combinations. So this is actually true. And the same thing, you can actually do it for the other way. Okay, so if we have A union with B and C, then it's the same thing as saying A union B intersecting A union C. Okay, I'm sorry, A union C. Yeah. I don't want to prove this to you guys, since you can just try and see, put the x's and then just try like I did for all cases. And then we have just proven that this formula is also true. So I hope you guys really enjoyed this video, and just had a small glimpse of how logic works and how set theory works. It's a bit difficult to understand in the first place, but actually it's a very easy thing if you have the abstract logical mind and commitment to understand it. So I hope you guys enjoyed the video, and we'll see us in the next Daishinfinity video. See ya.